So today we're going to be talking about galvanic and voltaic cells, also known as how we make batteries. So we talked earlier this year about redox reactions. Remember, redox is short for oxidation and reduction. Oxidation is loss of electrons, reduction is gaining electrons, which you should remember from the mnemonic oil rig. So we've got oxidation happening. We have a metal, and it's losing electrons and then becoming a metal ion. It's going to happen with nonmetals too. We're going to focus on metals because that's most of what we're going to be working with. And so our metal should actually lose mass because some of that metal is becoming ions. In reduction, we take metal ions and they gain electrons and then add on to our piece of metal because they're becoming part of the regular metal. So now what we've seen in the past is we just put a piece of metal in a different solution, and your electrons get transferred directly, and there's nothing we can really do with that energy. It just gets wasted because it's all happening in one place. In a battery, what we do is we separate our oxidation and reduction reactions, and we force those electrons to flow between the two. And that flow of electrons can give us a voltage, which gives us our battery. A couple of terms and a couple of conventions we're going to use with batteries. We set it up so that the oxidation happens on the left and the reduction happens on the right. And that way our electrons are going to flow from left to right through our circuit. We call where our oxidation is happening our anode. This metal is going to lose mass, and because our neutral metal is going to become positive ions. In our reduction side, we're going to call that our cathode. The metal is going to gain mass because positive ions are going to become neutral metal. Again, this can happen with nonmetals. We're mostly going to focus on metals because those are easier to build batteries out of. How we know how much current or how much voltage, that we can get is based on our standard reduction potentials. You saw this table when we did our simulation. More positive reduction potentials means it wants to get reduced. More negative means it's going to get oxidized instead. It's related to our activity series, if you remember that, but it goes kind of backwards from what we're used to. Our most active gives our most negative reduction potential. Our least active gives us our most positive reduction potential. It wants to be the metal, as opposed to our negative. It wants to be the ions. It wants to be oxidized instead of reduced. If we're going to calculate the voltage of a cell, so how much energy we can get out of our battery, we've got a couple options we can do. They're both going to involve looking at the table. What you'll see written most of the time is the energy of our cell is equal to the reduction potential of our cathode minus the reduction potential of our anode. Another way to look at it is if you don't want to worry about the labels cathode and anode, look at your table. The most positive reduction potential is going to keep its sign. The less positive or more negative reduction potential is going to get its sign flipped, and then you add the two together. And if we get a positive voltage when we do this, it means we've set our battery up correctly. It means it's thermodynamically favorable. It'll actually give us energy the way it's written. So let's do some math with this. We want to calculate the voltage of a cell made with magnesium and silver and figure out which element is going to be our anode. So we are going to look at that reduction potential table. You actually have one in your notes. That's not something you're going to have to memorize, just something you have to use. And so if we look at our reduction potential table, we're going to look up our two elements. So first we're going to look up magnesium, and we've got Mg with a 2+ charge plus 2 electrons gives us magnesium metal with a voltage of negative 2.36 volts. And then we've got silver, which according to our table, if we have silver with a plus charge plus an electron, that gives us silver metal with a voltage of 0.80 volts. We said our more positive number, that's what's going to be reduced. That's what's actually going to follow what it says. So our silver is what's getting reduced. So that is the cathode in this battery. Our magnesium's more negative, so that's going to be oxidized, which makes it our anode. One way to remember that, the vowels stay together, the consonants stay together. Now to actually calculate the voltage for our cell, we said that E cell equals E cathode minus E anode. So in this case, we've got our silver minus our magnesium. And so that's going to get us a voltage for our cell of 3.16 volts. It gives us a positive voltage, which means we've done everything correctly and we've made a good battery. You should try your guided practice on your own and then come back and check and see how you did. For our first guided practice, we want to calculate the voltage of a cell with electrodes of lead and aluminum. We have to figure out which electrode would increase in mass. So if we look at our reduction potential table, we will find half reactions for both elements. So lead, it gives us 2 plus 2 electrons, gives us lead as a metal with a voltage of negative 0.13 volts. And then for aluminum, aluminum ions plus 3 electrons give us aluminum metal with a voltage of negative 1.66 volts. Now we've got to decide who's being oxidized and who's being reduced. Our more positive actually gets reduced, but in this case, our more positive is actually negative. That's okay. Negative 0.13 is our bigger number, so that's reduced. If it's reduced, that means that will be our cathode. Our more negative will get oxidized, which will mean that will be our anode. Now to calculate the voltage for the cell, remember that E cell equals E cathode minus E anode. So in this case, that will be negative 0.13 volts minus a negative 1.66 volts for a voltage for our cell of 1.53 volts. And now we've got to decide which electrode is going to increase in mass. And so remember, you'll get an increase in mass if you're taking ions and making metal, which is our reduction. So lead, because that's going to stay reduced, lead is going to see an increase in mass because it is our cathode. And our last guided practice is a little different, but not too bad. We want to figure out what other element would be needed to make a cell with a voltage of 2 volts. 2 volts with copper as the cathode. So we know we've got to use copper, so let's look at our table. We find that copper has a voltage of 0.34 volts for reduction. And the other thing we know is our E cell, which is 2 volts. And we're going to plug this all into our equation. Our E cell is 2 volts. We're told that copper has to be our cathode, so we'll plug that in as our cathode, minus E anode, which we don't know. So now we've got to do our algebra. We're going to subtract 0.34 volts from both sides. That gives us 1.66 volts equals negative E anode, which means we've got to divide both sides by negative 1, which basically means we're flipping the signs. So our E anode value is going to be negative 1.66 volts. We will look that up on our table. We just used that one in our last problem. That's going to give us aluminum for our other electrode. So now you can either do your next set of notes, or you can work on the parts of the quest that you can do. Either way, ask questions if you need help.